Hello everyone, my name is Haomin from State Key Laboratory, Mechanical System and Vibration, Shanghai Jiao Tong University. It's a great honor to share some of my recent research work in this session. Today, the topic of my presentation is self-driven frequency sensing mechanism based on magnetoelectric composites. The whole presentation is divided into the following 4 sections. In section 1, let me introduce the research background, motivation, and the solution. Just as fingerprint identification can be used to determine the human's identity, model parameters, including frequency and the vibration modes, as dynamic fingerprints can also reflect the structure, health condition, which is widely used in the conditioning monitoring of the large-scale field structure, such as bridge, tunnel, and transmission tower. The acquisition of model information relies on stable and precise excitation. And generally speaking, the excitation sources are categorized into 2 types, hammer impact and shaker. Due to energy leakage and human errors, including double hits and the unstable excitation forces, the hammer impact test places extremely high demands on the operator. In contrast, although the shaker can accurately apply the excitation force of arbitrary waveform through the control signal, the installation of output rho changes the original constraint condition, thereby affecting the model parameter. In conclusion, the ideal solution would be one that achieves both controllability of the excitation force and the minimal impact on the original structure, and just like this table. Inspired by self-sensing magnetostructive actuator, we propose a self-driven frequency sensing mechanism based on magnetoelectric composites. The proposed mechanism combines magnetostructure's high energy density and achieve driving characteristic with piezoelectric ceramics high sensitivity and a superior dynamic sensing performance to break the limitation existing in the traditional excitation method, which also provides a novel solution for the online acquisition of structure and model parameters. Section 2 will provide a detailed explanation of sensing mechanism from the perspective of dynamic modeling. The following magnetoelectric, magnetostructive, and the piezoelectric will be referred to using abbreviation. The basic sensing mechanism is illustrated in the flowchart. First, MS phase will deform under the excitation magnetic field generated by driving coil, which drives the shell to vibrate accordingly. Next, the inertial force generated by shell vibration will be transmitted to beam through the output rod, which causes the beam's transverse vibration. Then PE phase will convert the interaction force between MS phase and the beam into a voltage signal. Finally, the beam's natural frequency offset under the action of external force effects can be directly characterized by the PE phase and the output voltage. Comprehensively characterizing magneto-mechanical electro-multiphysics coupling is the key to establish the dynamic model of ME. On the one hand, considering that the interaction force between MS phase and a beam is small, the PE phase is described by a linear constitutive equation. On the other hand, to account for the hysteresis nonlinearity, the MS phase is modeled through a nonlinear constitutive equation based on the modified JA model. However, due to the bidirectional interaction between the stress and magnetization, the magneto-mechanical coupling relationship must be supplemented with the appropriate elastic boundary conditions. In addition, using equivalent magnetization to represent the magnetization distribution along the MS phase axis can significantly improve the computation efficiency. In order to further explore the relationship between the extra tension and output voltage of ME phrase, the system dynamic model is established according to the above physics model. The system consists of 5 parts, and a different equation of motion of each part is formulated as follows. The nonlinear terms in the constitutive equation of MS and the PE phrase are written into the differential equation through the stress-strain relationship. Section 3 will verify the reliability of the purpose sensing mechanism through a prototype. The experiment will be carried out from 3 aspects. First, the parameter in the system dynamic model can calibrate it to improve the simulation accuracy. Then the beam transverse natural frequency offset under different extra tension is measured online by applying a swap frequency excitation. Moreover, in order to solve the contradiction between the frequency resolution and the scanning speed, further research is carried out on improving sensing efficiency. The prototype test platform is shown above. The power amplifier amplifies the control signal generated by the locking amplifier and input it into the driving coil. The prototype's rod is fixed to the beam center point. The beam will be forced to vibrate under the excitation of MS phrase, Teflon D, and the PE phrase, PCT. Convert the beam vibration into a voltage and output it into the locking amplifier. The extra tension applying to the beam by the tightening the nuts can be directly measured by the force sensor. The system's structure and the material parameters are directly obtained by measuring and checking table. Partially constitutive parameters of MS and the PE phrase are modified and calibrated according to the resonance frequency and the quality factor. As shown in the picture, the simulation results can accurately predict the system amplitude frequency response after parameter calibration, which lays a theoretical foundation for the subsequent experiment. As shown in the left picture, the beam's first-order natural frequency increases with the extra tension Fx. When Fx increased from the 45.3 Newton to 95.7 Newton, the beam natural frequency is shifted by 2.7 Hz. The sensitivity and coefficient is the 0.045 Hz per Newton. As shown in right picture, the consistency of the experimental and the simulation results verify the reliability of the purpose sensing mechanism. In frequency scanning mode, high frequency resolution often means long time. In order to improve the sensing efficiency to satisfy the dynamic measurement requirements, the variation of extra tension is measured by voltage amplitude at a specific frequency. In dynamic mode, the relationship between the voltage amplitude and the extra tension is nonlinear. The average sensitivity coefficient is minus 0.038 microvoltage per Newton. Finally, a conclusion of research content is provided. In order to avoid the measurement error introduced by human error and the alteration of constraint conditions in hammer impact and shaker, we propose a self-driven frequency sensing mechanism based on ME composites. The frequency sensing mechanism is reviewed by the system dynamic model based on the simulation results of theoretical model. The sensing performance test of prototype is carried out. The results show that the sensitivity coefficient of the prototype in the static and a dynamic model measurement are 0.054 Hertz per Newton and minus 0.038 microvoltage per Newton, respectively. Subsequent research will focus on the optimization of material composite configuration and the resonance mode to obtain the superior sensitivity coefficient. And that's all. Thank you for your attention.